Time crystals. We're all familiar with regular crystals, like salt or diamonds. Their atoms are arranged in a repeating pattern in space, a lattice structure. This spatial order is a hallmark of a crystalline phase of matter. In 2012, Nobel laureate Frank Wilczek proposed a mind-bending question. Could matter also exhibit a repeating pattern in time? Could there be a system whose lowest energy state, its ground state, spontaneously breaks time translation symmetry, meaning it exhibits periodic motion even without any external energy input? It sounded suspiciously like a perpetual motion machine, something forbidden by the laws of thermodynamics. The initial reaction from much of the physics community was deep skepticism. The second law of thermodynamics tells us that isolated systems tend towards increasing disorder, or entropy, eventually settling into a state of thermal equilibrium where nothing much happens. The idea of a system spontaneously oscillating forever in its ground state without dissipating energy seemed to fly in the face of this fundamental principle. How could a system be in its lowest energy state and yet still be constantly changing, constantly evolving in a periodic manner? It felt like trying to get something for nothing, a free lunch from the universe, which, as we know, rarely offers such deals, especially when it comes to energy. Many believed that such time crystals were theoretically impossible, a fascinating thought experiment, but not something that could exist in reality. However, the quantum world is full of surprises. In 2016 and 2017, several research groups independently announced that they had successfully created and observed time crystals in the laboratory. These weren't perpetual motion machines in the classical sense. They don't generate usable energy from nothing. Instead, these are specific quantum many-body systems, often driven by an external periodic force, that settle into a state that oscillates at a different frequency than the drive, a subharmonic frequency. This time translation symmetry breaking means their properties repeat in time, but not because they are simply following the external drive directly. They have their own intrinsic, robust temporal order. This discovery has opened up an entirely new field of non-equilibrium physics and new phases of matter, challenging our understanding of thermodynamics in driven quantum systems and potentially leading to new technologies in areas like quantum memory or ultra-precise clocks.